In this lesson, we will identify restricted values, the domain, the X-intercepts, and the Y-intercept for a rational function. So we're going to begin by exploring this f of x function here. And we are going to find some indicated values that have been selected for a good reason. The first thing we're going to do is find f of 0. Remember, that simply means we're going to substitute 0 in place of x and then just perform the arithmetic. We end up getting 1/2. Now, if you think about this, what significance is this? If the x value is 0, then this represents the point 0, 1/2, which lies on the y-axis. So this is how you would go about finding the y-intercept. Simply substitute 0 in place of x, and this is where your function crosses the y-axis. In the next example, we substitute -2. Why -2? Well, something interesting happens when we substitute -2 into the function. We end up getting 15/0, which is undefined. So we have 0 in the denominator when we substitute -2 into this function. This undefined place is going to represent a vertical asymptote. So this function is not defined at -2. So we would have to say that this function is restricted in that x can never be -2. The function will not exist at x equals -2. We'll have to remove that from our domain. Something similar happens when we substitute 3 into the function. But this time we get 0 in the numerator and denominator. We'll learn that this is an indication of a hole in our graph at x equals 3. So we have two values for which the function is undefined. We will remove -2 and 3 from our domain. So again, -2 and 3 were just given to us, but how do we find them? Well, we find them when we look at the factored form of the rational function. So here we have the same f of x function, but the numerator is factored and so is the denominator. So what do you notice about the results of 2 of the 3 function values above and the factored equations? Well, we notice that we got undefined when x was -2 and when x was equal to 3. So let's look at how that equates here. Then the -2 comes from setting x plus 2 equal to 0 and solving. And the 3 comes from setting x minus 3 equal to 0 and solving. Now, the x minus 3's, if we were simplifying this, would cancel out. That's how I know there's a hole there. We can take our numerator, just this part, 2x plus 1, since x minus 3's cancel, set that equal to 0, and get our y-intercept. So what we know is when x is equal to -2 and x is equal to 3, f of x is undefined. And that simply comes from setting your denominator equal to 0. So now we'll define a restricted value. A restricted value is a value of x for which there is no y value. The function is undefined at this particular x value. This is an @ symbol. So -2 and 3 are restricted values. Those are points that have to be taken out of the domain because the function does not exist there. Let's look at a graph of f of x to confirm all of this. We see that at x equals -2, there is a vertical asymptote. The function does not exist there. We see that at x equals 3, there's a hole in the graph, just a hole. All right, removable discontinuity. We also see that the graph crosses the y-axis at 1/2, just like we calculated. So it says here to describe the graph of f of x at its two restricted values. So we would simply say at x equals -2, the graph has a vertical asymptote, and at x equals 3, the graph has a hole, point discontinuity. So our domain, while normally we would like for our function to be from -infinity to +infinity, we do have to remove -2 and 3, and so the domain would look like this. Wondering where my stuff is here. It's a little slow. I'll just be patient. All right, on this page it says study the graphs of the 5 of the functions below. Clearly, one function is different from the other 3. Identify this function and state 5 ways that this function's graph is different from the other 3. So if you look at these graphs, we see that the h of x is different because it has 3 pieces to it instead of just 2 pieces like the other functions. All right, so h of x has 3 pieces where the others only have 2. Okay, the other thing we see is h of x doesn't have a hole. F of x has a hole at -6. G of x has a hole at -1, and P of x has a hole at -3. But h of x does not have any holes. So that's why h of x does not have point discontinuity. That's a fancy way of saying it doesn't have any holes. H of x has a range of -infinity to +infinity. It does have a horizontal asymptote, as the others do, but this middle piece actually crosses over the horizontal asymptote, which is kind of interesting. So because of this middle piece, we see that the range has no discontinuities. The range just goes from -infinity to +infinity nice and smoothly because of this middle piece. H of x crosses the horizontal asymptote. The others do not. So you'll notice on f of x, we have this horizontal asymptote and the function. So the range does not exist at about 1/2 for the y value. G of x, we would have to remove 2 from the range because the function does not exist when the y value is 2. And P of x, we would remove 1 from the range because the function does not exist at 1 for the y values. H of x has 2 vertical asymptotes. The others only had 1. Here we have a vertical asymptote at -5 and also one at +2. H of x has a point of inflection in the middle piece. You can see how it changes from concave down to concave up. So we know in here somewhere in the middle, there is a point of inflection. H of x has 2 zeros and the other have 1. So we see that it crosses the x-axis at -2 and 3. And the other graphs only cross the x-axis once. F of x crosses, somewhere around 6. G of x crosses the x-axis somewhere between 2 and 3. And P of x crosses the x-axis at -1. But H of x crosses twice at -2 and +3. So if you need to pause the video and get that list together. Okay, this page is sideways, so that's going to be a little interesting for us. So let's see, what are we supposed to do here? So Over the next few lessons, we will learn how to develop the graphs of rational functions and understand the connections between the equations of the function and the graph of the function. We will begin in this lesson to determine how to find the restricted values, the domain, the x-intercepts, and the y-intercepts of the graph of the function, and identify the following characteristics using the graphs from the previous page. So these are f of x, h of x, g of x, and p of x from the previous page. So the first thing that you're going to do is rewrite the function in factored form and identify the restricted value. So you'll see the function factored. The restricted values, remember, come from setting your denominator factors equal to 0 and solving. Then you'll identify the domain, which will be everything from negative infinity to positive infinity, except for your restricted values. So you got to take out those restricted values. Set each non-canceling factor of the numerator equal to 0 and solve for x. This is going to give us our y-intercept in this next column here. So now it says, what are the zeros of the, this gives us the zeros. So this would be the x-intercepts. So we're just simply stating that in the next column. So we get this answer from the previous one. It says, what is the value of the constant term of the numerator over the constant term of the denominator? So the constant term would be in f of x 36 over 0. Since there is no term in the denominator that has no x's with it. So the constant term is undefined. This simply means that there is no y-intercept. In the others, we can find the y-intercept by taking the constant term of the numerator divided by the constant term of the denominator. And remember, you can always go back and verify these facts by simply looking at your graphs. So if you want, I am including the key in today's folder, so you'll be able to see if you want to go back and look at this a little bit better. I apologize that it's sideways. Works better when we're doing this together in class. So now it says, study the information you found in the table to respond to these questions. From the equation of the rational function, how do you determine the restricted values? To determine the restricted values, you're going to set the factors of the denominator equal to 0 and solve for x. Now remember, this is after you have factored your polynomials, your numerator and your denominator. From the equation of the rational function, how do you determine the domain? Well, the domain will be all the values from negative infinity to positive infinity, except for the restricted values. So just remove those points from your domain. From the equation of the rational function, how do you determine the zeros? Set the non-canceling factors of the numerator equal to 0 and solve for x. And finally, from the equation of the rational function, how do you determine the y-intercept? You can simply take your constant term of your numerator and the constant term of your denominator and divide them. This says divide the constant term of the numerator by the constant term of the denominator. And now you get a chance to practice. So if you want, pause the video and see if you can answer these questions for f of x and g of x. So the first thing we do is factor f of x and g of x. When we set the denominator equal to 0 in f of x, we get x equals 3 and x equals negative 1. So our domain is from negative infinity to negative 1, from negative 1 to 3, and from 3 to infinity. Always using parentheses here to indicate that we're leaving out negative 1 and we're leaving out 3. The 0, since x minus 3 cancels out, we set 3x plus 2 equal to 0 and solve, and we get x is equal to negative 2/3. This is our 0. This is where the function crosses the x-axis. For the y-intercept, we take our constants, negative 6 divided by negative 3, which is 2. This graph will cross the y-axis at 2. That's the point 0, 2. For g of x, we factor. We set the denominator equal to 0. We get negative 2 and 2. So our domain includes everything from negative infinity to infinity, except for negative 2 and positive 2, and we write that thusly. Since x minus 2 cancels out, we set x plus 5 equal to 0 to find our x-intercept, or the 0 of our function. This graph will cross the x-axis at negative 5. To find the y-intercept, we divide our constants, negative 10 divided by negative 4, and get 5/2. This graph crosses the y-axis at 5/2, which is 2.5.